So last time I was discussing about the amplifier, uh, amplifying the one of the laser modes, the resonance frequency modes, and I was discussing about also the bandwidth of the amplifier in compared to the bandwidth of the resonance frequencies. And I should stress that always the bandwidth of the amplifier is larger than the bandwidth of the resonant frequencies. And also it is possible that this bandwidth might be even larger to include more than one resonance frequencies. And in that case, what happens is that the laser feeds two different frequencies. So it's going to be not monochromatic. Uh, well, uh, in the sense that even if the amplifier feeds, let's say, two frequencies, if you look at with your own eyes that these two frequencies, you will not discriminate the color. You will see that these two frequencies are close to each other so that you cannot tell that these two are different colors. But nevertheless, still there is some difference between these resonance frequencies, and at least you can say that the laser is just um, using more than one frequency. What happens in that case? If your laser is using more than one resonant frequency, I mean, it resonates 2, 3, 4, 16, whatever number of frequencies, your laser turns out to be a pulse laser, okay? And I will discuss today how this pulse laser works and some of the characteristic parameters that tells about the pulse width and etc. The frequencies of a pulse laser. So let's start with this usual single frequency laser and what we have in a single frequency laser. What you see in both the time domain and the frequency domain, and this is an ideal laser that the time domain is perfect sinusoidal wave. What this wave is about is the electric field of the light. Okay, it's perfectly oscillating without changing its amplitude, etc. over time. So, in fact, this is not a wave train. You should understand this wave goes to infinity in both directions. Okay, so the corresponding frequency domain representation is this, since it's a very uh, long, infinitely long wave train, we will have a sharp, infinitely sharp single frequency. And this corresponds to if you take the square of this electric field. So how do you calculate the intensity? To calculate the intensity is just to take the square of the electric field and take the time average. When you take the time average, you will obtain this constant signal as the output signal of your laser, output power of your laser. Okay. Well, if you take the square of this sinusoidal wave, of course, it's going to be again sinusoidal, but uh, uh, the peaks will be denser, twice denser than this one, amplitude view. And the other thing is that when we take the square, after that, we take the average. When you take the average, time average, you get this plain, constant output as the intensity of your laser, single frequency laser. Okay. And what if you get, as I said, your amplifier feeds two different frequencies? If the amplifier feeds two different frequencies, that means that your electric field look like this. You have two sinusoidal waves, but with different frequencies. But the thing is that these frequencies are very close to each other. I mean, even this picture is, tells you, you can see immediately that there is difference in the frequency. but in fact, in reality, the difference between these two frequencies is very, very small. Okay, when you have very small frequencies, difference frequencies inside the laser, anyway. So if you want to get this output, you should add these amplitudes. Okay, you should add these amplitudes of two different frequency light. What you get, obtain this bits. Okay, so this signal is just the mathematical addition of these two different frequency amplitudes. Okay, when you add this, you get this. So you see, what you see in this picture is that it's a beat. We call this beat. Okay, looks like a heartbeat. Okay, you have this again oscillations, um, and the oscillations of these peaks, okay, is just the average of the frequencies of these two different frequencies. So it's going to be very much close to one of the frequencies, okay, because they are very close to each other, these frequencies, F1 and F2. And the frequency of these peaks, these small peaks, sorry, the changing amplitude peaks, you see, there are peaks again, looks like very periodic. It's in fact, it's periodic. The frequencies of these peaks, changing amplitudes, is nothing but F1 plus F2 divided by 2. It's the time average of this. But also, what you see is that these peaks are increasing and decreasing periodically. Okay, the amplitude of these peaks are increasing and decreasing periodically. Sometimes it gets even almost zero, and sometimes it gets a maximum value. So this goes on periodically. Okay. Uh, what you get is that if you just connect the peak points of these oscillations like this, you get an envelope. Okay. Let me read this. If you if you just connect these, you know, these peaks, all right. If you connect these peaks, you get an envelope like this. This is called envelope. This is also, in fact, this line, this imaginary line, also nothing but an oscillating behavior. Okay, it's a sinusoidal. Okay, so what we get, in fact, is that in that case we have a bit. Bit has its uh, frequency, larger frequency, which was the average of the you know additive frequencies, and also it has this envelope. Okay, this envelope again, another sinusoidal wave. Its frequency is going to be difference between these two frequencies. So the wave is larger, but the frequency is going to be very small in compared to the small peaks frequencies. In that case, if you just uh, curious about what is going to be the frequency of this larger envelope wave, it is going to be just difference between these resonant frequencies, F1 and F2, F2 minus F1, etc. Okay. Anyway, so what happens if you take the square of this signal to obtain the intensity? Okay. When you take the square and take the average, what you obtain, in fact, now is not a constant signal. Okay, you will have an intensity which is itself again a sinusoidal varying power. Okay, this is what you get if you take the square of this bit and take out time average. You obtain this output signal. Okay, so in that case, what you observe from your laser is that your laser will not shine continuously, but it will flick. It will be flickering. Okay, it's like a flashlight, but it's going to be very, high frequency. And the period of these peaks the period of these peaks, if you just want to ask what is going to be the period of these peaks, it is going to be given by this formula that period T is 1 over Fs. But 1 over, what is Fs? Fs is nothing but the frequency difference between the resonant frequencies, two resonant frequencies in that case. Our laser is a two-mode laser. It is a two-mode laser because the laser feeds two resonant frequencies, and it's lasing in two resonant frequencies. So Fs is nothing but the difference, frequency difference between F1 and F2. And if you take the inverse of that, what you will obtain is the period of the output intensity. Okay. Well, you can prove this if you are clever enough. Then you can just sit down and calculate how these are going to be. You get this period. It's easy. I mean, just assign cosines or sines to these waves and add them all, and then do this. You will obtain anyway this. So I'm just showing you the result. All right. So your laser is not a continuous wavelength laser anymore. Your laser is a pulsed laser. Why? Because the output comes with pulses. The output of the laser comes as flashlights. It's pulse. They're pulses. Your heartbeat is pulsing. Okay, you know this, and many of the things in nature also show this kind of behavior. And your laser, your pulse laser, is beating. All right. Okay, so well, you're not, of course, just constrained to have only two resonant frequencies. You might have more than two, like in this picture. In that case, you have three lasing frequencies. Also, these all three lasing frequencies are fed by this amplifier bandwidth. So amplifier bandwidth has this very wide bandwidth, and inside it you have these three resonant frequencies, and all of these three resonant frequencies under this bandwidth, amplifier bandwidth. That means they are just fed by the amplifier. That means inside between these two mirrors, you have three different frequencies of light, which is resonating and which is lazy. So this is also possible. I mean, any number is possible. So let's think about three. If you add these three, which are different frequencies, but again, the difference between the frequencies is just the same for all of them, okay, Fs. And these are the time domain pictures. And when you add them, what you get? What you get when you add them, again, it's going to be a bit, okay? Having this envelope period, again, it's given as just with the same with that of the previous one. Again, it's 1 over Fs. Okay, this it doesn't change. Again, this Fs is just the difference between successive resonance frequencies. So, but what you obtain this time is that this time, in compared to the previous case, the output peaks, width of the output peaks is smaller. Okay, you see the width over here for the two frequencies, and this one, and over here, this width is getting narrower. Okay, if this getting is narrower, the peak value, this peak value is getting a larger, higher value. Okay, this is not shown in this picture. It's not scale to scale, but you will understand that as you get these pulse widths narrower and narrower, you obtain the maximum value of the output intensity is larger and larger. Okay, this is what happens. Okay, so what you see, in fact, you squeeze kind of. You squeeze the peaks, you squeeze the packets. You squeeze the packets, they get narrower, but they get higher in length, in the height, okay? So you get higher power. That means higher peak power. I mean, this power will not survive continuously. It will drop to zero and some small value, and again, maximum value, etc. It will go like this. But the thing is, the peak power is going to get larger and larger. Even this peak power survives shorter and shorter in time. The peak power is going to be larger, but this is the main point. I mean, if you have a laser, a pulse laser, when you're talking about its power, what you're talking about is in fact the peak power. Okay, it's not the average power. So if you get the idea that if you want your pulse laser to have higher or larger peak powers, so this is the recipe that what you get is you have to feed more and more different frequencies. You have to feed more and more different resonance frequencies. Okay. So let's observe the next one. This is the picture for adding two resonance frequencies. This is 3, this is 4, this is 8. So as you each time you increase the number of resonant frequencies, observe that how these widths of the pulses are getting narrower and narrower. But at the same time, since this is not to scale, you will not see this very well. At the same time, when you get the narrower bandwidths, your peak values is getting a higher value. Okay, peaks are getting higher and higher as the bandwidths are getting narrower and narrower as the number of resonance frequencies are getting higher and higher. So this is what you get. And in this picture, what you see is you get the picture for 16. You get the picture for 16 different resonance frequencies. They're all fed by the amplifier. And you observe how these, widths are getting even narrower and narrower. And so, and also, what you get, of course, the period of these peaks is getting, you're getting uh, from the same formula, or whatever your frequency difference between the resonant frequencies. But of course, if you get the larger and larger number of frequencies, their differences, successive differences, will get smaller and smaller. If these are getting smaller and smaller, then the period of these peaks is going to get larger and larger. So there is this inverse relation. Okay. Well, next question you should ask. Okay, what about this pulse width duration? I mean, the what about this halfway? You go the halfway through this peak power and just measure the width of the power. Let's call this tau p. Okay, this is the width of the pulse width, and it is given by this formula. It is 1 divided by. Let me put this in a larger font. The peak power. Sorry, the pulse width is nothing but 1 divided by the number of, let me put this over here. It is the 1 divided by the number of resonant frequencies. Well, for example, for this example, it's 16. This N, capital N is 16. But for this one, for example, this is 4, just 4. However, whatever this number of resonant frequencies multiplied by Fs. It is just the difference between the resonant frequency. This will give you the pulse width, okay? The width of this, one of these pulses in your laser. So as you can, imagine, or you can find that as the number of resonant frequencies is getting larger and larger, this pulse width is going to get smaller and smaller. Even with this, you get the peak power getting larger and larger. Okay, so that way you reach femtosecond lasers. These femtosecond lasers are the uh, the highest technology pulse lasers, and they are used. Femtosecond laser used in many applications, like as we have discussed, the applications ranging from the medicine to military. because whenever you need, even in this industry, whenever you need very high peak powers, this is what you get. You have to get, if you require very high peak powers, you have to get a pulse laser. Continuous wavelength laser will not do the job for you. You have to, obtain this class of lasers, which are pulse lasers. And in fact, at the beginning of this technology, these pulse widths like on the order of nanoseconds, but we reach out now the order of femtoseconds. Okay, femtoseconds are very short. 10 to minus 12. You just receive a signal which lasts only in the order of 10 to minus 12 seconds, which is the fastest signal that you can obtain man-made. Okay, so I mean these will have very good and high application ranges, having this kind of property with this kind of very high powers, high energies, etc. We use in many applications. Okay, so this is it. This is the idea behind this pulse laser. Okay, and well, if you ask me if which one is more, or continuous wavelength or pulse lasers are most frequently used, it depends on the applications. But as I said, if you require high powers and if you require fast devices, what you get is pulse lasers. Okay, so next question is, okay, where can we find all these frequencies? Of course, all these frequencies are available between two mirrors. Okay, these frequencies are available. But ask yourself this one. Suppose you have a laser which has these two mirrors which are separated by a distance L, and suppose this is your resonant frequency modes of the laser, and if you just put your amplifier between these mirrors, well, you will also get this amplifier bandwidth, which is shown as an umbrella over here. And in this picture, what you observe is, in fact, is four-mode laser, okay? Because the amplifier just feeds four of these resonant frequencies. So, can you get, without changing your amplifier, can you get more of these resonant frequencies under this umbrella? So ask yourself, how can you get more frequencies under this umbrella, or within the range of amplifying region of this amplifier? How can you get it? How can you do it? You have four, but you want, let's say, eight. So if you want to get, without changing the amplifier, if you want to get more of these resonant frequencies, what you get, in fact, is just change the parameter. Well, what you see over here, the difference between these frequencies ranges as 1 over L, which is inversely proportional to the distance between the two mirrors. So if you increase the distance between the mirrors, think what you get. What you get is this difference between the successive resonant frequencies will decrease. If you increase L, the difference between the successive resonant frequencies will decrease. That means you will obtain higher number of resonant frequencies under this umbrella. Okay, if you double, now with this picture, if you double the length L, you get 8 of these resonant frequencies under the same amplifier bandwidth. Okay, this is the way. Okay, so there are methods to obtain the higher number of resonant frequencies in succession. In turn, you will obtain a higher peak power, and you will obtain smaller pulse width, etc. This is the recipe. Okay, you get larger and larger sorry, uh, mirror distance, or larger, longer path length of this lasing beam going back and forth between these two mirrors. So, well, if you have a limited space, what can you do? Well, if you have a limited space, There is another way to increase this path length, which is L over here between the two mirrors. If you just put a third mirror somewhere over here, okay? If you put a third mirror somewhere over here and just tilt these mirrors so that your uh, laser light will just form a closed loop like this. It will go around this cavity of three mirrors like this. Well, in that case, you just increase the path length L, okay? If you use three mirrors, and this is possible, you are not limited to only two mirrors to construct a optical resonator. Optical resonators are just closed loops. You're not obliged to have only two mirrors. You can have more than two mirrors, okay? So you increase the path length, you increase L. So if you in a limited area, you can use higher and higher number of mirrors to increase this path length more and more so that you have more and more resonant frequencies under the same amplifier bandwidth. So very highly developed commercial uh, pulse lasers uses four mirrors, five mirrors, etc. They never use only two mirrors, okay? Because in order to get the more resonant frequencies under this given amplifier bandwidth, you require more resonant frequencies. What you should do is you just increase this path length L, and this is what you should do without in a limited place. Simply, you cannot have a laser which is, let's say, 50 meters long, right? Or 10 meters long. It's going to occupy a very large space in your laboratory. Even if you get a portable device you want to get out of this, you have a problem. Okay, so uh, in very highly developed pulse lasers, you will see three, four mirrors inside the lasers. And well, there is one drawback to increase this number of mirrors inside lasers. There's one disadvantage. Of course, the advantage is, of course, you get the narrower pulse width, higher peak power, etc. You know this. But if you increase the number of mirrors, you will face with some very highly delicate alignment problems. Okay, doing the alignment of this laser, which has three or four mirrors, is going to get the longer time. Is harder. Okay, because you will instead of just adjusting two mirrors side by facing each other, this time you have to align three mirrors, four mirrors, etc. It's getting uh, more difficult, right? So the, I will tell you a story about myself that I was working in a experimental group. I was in Germany during my PhD, and this group was, working on a pulse laser, which had, I think, four mirrors, etc. They just bought. But the thing is, when you buy these kind of lasers, the technical stuff will come that the company technical stuff, they will construct the laser in your laboratory. It takes time. It's not a package. Get it and unpack it and just press the button, run it. This is not the way that you do with these highly complicated pulse lasers. So they came and they just stay in the city because they were coming from a different city. To adjust these mirrors of the laser, they just we bought. They just spend 1 week time to adjust the mirrors. 1 week, so it takes time. It's not that easy to align the mirrors because they have micrometers, micro range translators inside this mirror. Because even uh, maybe nanometer of difference in the location in the mirror makes difference. Okay, So it takes very high, very delicate tools to adjust these mirrors. So because of this, very highly delicate dependence on the position of the mirrors, these lasers are put on the optical tables. Did I show this during my lectures? I don't. We have one of the optical tables in our lab. I think I showed you. Anyway, these optical tables are very heavy. I mean, the one which we have, I think it was just 500 kilograms, half a ton. Okay, you require very heavy platforms to locate these lasers because even very small vibrations on the ground that you can never just feel it. Okay, there's always a vibration in the ground. It will just cause maybe damage, or it will cause disturbance on the output of these kind of lasers, because as I told you that the location of these mirrors are very, very delicate to operate the lasers. Okay, that's enough for uh, increasing. Well, of course, for example, to have a pulse laser producing a pulse signal output power like this, uh, combining these 16 different frequencies are not enough. You have to do something more. You have to add all of these 16 different frequencies. Just they must be just in phase. What I mean by in phase? Sorry, I beg your pardon. Okay. So I was telling you that in order to get these beats, or the pulse lasers, you have to just add different frequencies like this. But there is one very important condition to have this kind of output, very neat and periodic and same power. You see over here, each peak has the same power, a regular power. In order to get this signal, there is one crucial thing you have to do. All of these uh, resonant frequencies, resonant lasers, must start, they all must start just in phase. They must start in phase, in time. What do I mean by in phase? Do you know what in phase? What is a phase? The phase is the location of these peaks or dips for a sinusoidal wave. Okay, wherever these are located, if you know where these peaks are located or dips are located, you just know the phase of the wave. What I mean by in phase, they all must be in phase. You just pick up a fixed time for all of them. At this time, at the beginning, let's say, if one of the waves starts with peak, all of the others must start with peak. Okay? If it starts with the dip, they all must start with dip. This is what it means to be in phase for all of the waves. Okay? Eş fazlı olmaları lazım. Eş fazlı olmaları için birisi maksimumla başlıyorsa diğerlerine maksimumla aynı anda başlaması lazım. Veya minimumla başlıyorsa diğerlerinin hepsinin aynı minimum olması lazım. Eğer birazı maksimum, birazı minimum ya da işte ikisi arasında bir yerde başlarsa ne olur? What happens if you don't have all of these, let's say 16 frequencies, not just in phase? What you obtain is this output. Okay. If you start all of these 16 different frequencies, they're all in phase, you get a very neat, very good peaks. They all equal themselves, equal each other, and they all well-defined period, etc. This is very neat. But if out of these 16 frequencies, only 10 of them starts in phase, this is what you obtain. Okay, neither their peak power are just close to this one. They are very low peak powers, half, even not half of them. And in between, you don't get a zero signal. This is also important. You should get a zero signal in between, almost zero, let's say. But what you observe over here is that is nothing but a noise. Okay, it's a noisy output. It's You cannot tell that it's perfectly periodic, and also their peak powers are not as large as these ones. So, adjusting these mirrors also requires, to get also all of these lasing frequencies uh, lasing in phase. You're not only adjusting this location of the mirrors, but also with this tilting the mirrors, you do this phasing. Okay, and this is called this is there is a technical term for this. This is called mode locking. Let me write it over here. Mode locking. Okay, you just lock the modes, all the modes. What I mean by modes is that frequencies. All of these frequencies are called modes. Okay, they're the modes of the laser. You have to lock these modes so that they all start with the same signal, with the same peak, or with the same phase. This is called the mode locking. Without mode locking, without you do your locking the modes, you cannot run the pulse lasers, and forget about it. And I tell you, it's very tedious task. It's hard. Okay. All right. So what's next? There is also another thing, phase lock, or mode lock. The phase lock also is another term, but they're the one and the same. Okay. It's so far so good. You have just make a difference now. What are these resonant frequencies? What is the amplifier? What is the amplifier bandwidth? What are these resonant frequency bandwidths? And what is having a multimode laser to construct uh, pulse lasers? And make a difference between the pulse lasers and continuous wavelength lasers. Okay, so all of this, but you don't know how to start a lasing or optical resonator to lase. As I said, these mirrors are important. That sometimes the amplifier just fills all of the region between the two mirrors. Okay, the mirrors are just located on the faces of this amplifier region. If this is a solid state laser, this amplifier is nothing but a crystal. And if we shave the ends of the crystal and just cover with some very thin layers of metal, you can construct your mirrors on to the same material that you have this amplifier crystal. Uh, but the thing is, uh, what you usually see for crystal lasers, the amplifier to be crystal or solid state lasers, they cut the crystal like not perpendicular to the beam, but some angle cuts like this. They do this. And I will explain why do they do this. Okay, I will explain why do they do this over this picture. Well, uh, there is also this property of the light that we call polarization. Light is polarized or unpolarized. If you have a polarized light, what do you mean is that, remember, the uh, single frequency light or laser has this very well defined electric field which is oscillating. Let's say I'm drawing these oscillations in the plane of the paper, and it's oscillating in this direction. Okay, on this or this axis, they're oscillating back and forth on this line, direction of this line. Okay, but you might have very well this oscillating direction for the electric field, not in this axis, but in an axis which is perpendicular. It might be perpendicular to the plane of this paper, or they might oscillate along this line. They might oscillate on this line. So what this oscillation line or direction for the electric fields defines the polarization of your light. Okay. So for example, if with your perspective, this is the oscillation direction for your laser, let's say, we say that your laser is just polarized perpendicularly. Okay. But if the electric fields are oscillating, let's say, in this direction, direction which is perpendicular to this plane of the paper, this time we just say that the laser is just polarized parallelly. Okay, this is perpendicular polarization. This is parallel polarization, where whatever you might call it, certainly you have two perpendicular direction for the polarization. So independently, there is two independent polarization direction for each laser light. Okay, and this is just, as I said, the direction of the oscillating electric field. Certain line, along certain line, the electric field oscillates. But sometimes you can have two independent oscillation direction, not more than two, for linear polarization. This is called linear polarization. Okay, linear polarization means that your electric field is just oscillating on a line. It's linear. Okay, even in this direction or whatever it is. But also it might be just case that your electric field, as let's say this is the direction of the oscillation of the electric field and it goes towards you, and I'm just sending toward you a laser light. The direction of the oscillation direction of the electric field is just perpendicular, it comes to you. Or I can send you toward you a laser light which is in this shape, that electric field is just oscillating parallelly. Okay, this is also the case. There is also one other oscillation property. As the light propagates toward you, the direction of the oscillation line for the electric field might change. As the light propagates toward you, you see the oscillation line for the electric fields are rotating. It might change its oscillation direction towards you, even they can turn in the clockwise direction or counterclockwise direction, like this. And this kind of light is called circularly polarized light. Okay, and there are many different combinations of polarization for the light, as I said. So one is that the linearly polarized light, and the other is circularly polarized light. Okay, and also for this circular polarized light, there is two independent circular modes. One is clockwise, and the other is counterclockwise. The electric field rotates in one way or the other way. They are independent. Okay, and it's called circular polarization. Okay, most of the light that coming from change of the energy level between these energy levels of the electrons produces circularly polarized light. And the other thing is that you might ask, can you convert, for example, circularly polarized light into linearly polarized light? Yes, you can. You can convert through some optical elements, some crystals, etc., some plates, etc. You can convert a circularly polarized light to linearly polarized light. But there is one thing that you cannot do. For example, if you have a vertically polarized light, you can never convert a vertically polarized light into horizontally polarized light, because they are perpendicular to each other and there is no way to produce a horizontally polarized light out of this vertically polarized. But if you have a 45-degree polarized light like this, you can convert this into a horizontally polarized light by just putting a filter. You can convert this 45-degree polarized light also into perpendicularly polarized light by putting a filter, because this direction of the polarization has projection on the horizontal direction, also it has projection on the vertical direction, but you can never convert vertical into parallel or parallel into vertical, horizontal into vertical. So these are usually denoted as capital V and H for linearly polarized. Whenever you see V, that means that light is vertically polarized. Whenever you see H, that light is horizontally polarized. Okay. If you see this, your light is right circular. If you see this, your light is left circular. This is R and this is left. These letters denotes the polarization of your light. I beg your pardon. Okay. Sorry about this. Okay. Now, these are the letters. Whenever you see in an optics textbook, you will see on the under the polarization of a concept, you will see these letters. L is left polarized, R is right polarized, and H is horizontally polarized, V is vertically polarized. So I was talking about, why do use this kind of cutting, angled cutting for the crystals as they put in the as an amplifier inside these lasers. Well, if you cut these ends of the certain angles, of course, not any angles is works. Certain angles of these are called Brewster's angles. Okay, let me also write this. As these angles are special, they're called Brewster's angles. If you cut the endpoints and faces of the amplifier like this will serve to produce a laser light to have a certain polarization. Okay, with this, your output is going to be either horizontally polarized or vertically polarized. But with this, with no any cutting, your output is going to be mixed. Your output will contain the polarization of any direction. Okay, your output will contain, well, of course, they're going to be the same frequencies, but if it's a single mode continuous wavelength laser, but the polarization of every photon is not going to be the same. All photons are going to be polarized in certain different directions, mixed. But if you do this, you produce also a single polarized output for your laser. Okay, this is what you should do. All right. So if you have questions, you may ask anyway. Uh, I'm recording this here. So the next thing is I will discuss you about how this amplifier that you put inside or between the mirrors or inside the laser. Okay, but before this, I have to you know uh, define some of the concepts. That suppose you have an amplifier like this in this picture. Okay, uh, or let's say the box. Okay, it's a black box in some region or some place, some device that you don't know how it works, but you know the input and output. If you send light like this, having this amplitude as an input to this box, but you observe the output not changing its frequency or period, but it's changing its amplitude, getting a larger amplitude. And you say what this is that it is amplifying your light. So in that case, this medium, this material, this piece, or whatever it is, box, it is an amplifier. Okay, if you see this input and output, this is nothing but an amplifier. But if you if you see this that other way around, the inverse, that you send light with certain amplitude as an input, but at the output you observe that nothing changed but the amplitude just drops to smaller value, then you have an optical absorber. Okay, so what it means that, it absorbs some of the energy, right? It absorbs some of the energy so that you now have a lower uh, power light, because the amplitude of the electric field is small, but nothing else changed. I mean, the frequency is not changed. Maybe if there is a polarization, but polarization is not changed, nothing else. Only the amplitude changed. So in that case, your material is an optical absorber. It is absorbing, okay, the energy. And in the previous case, it is amplifier. This is amplifier. This is absorber. This is amplifier, absorber. Okay. So, but in fact, you just, you're curious that what happens in fact, what happens inside. Okay, what's going on? Why do we have this electric field? The amplitude drops for the absorber. Well, what you do microscopically, if you're just analyzing the picture, that you send some light. This light has some power. If the light has some power, that means it has some number of photons in it, right? Let's say two. And then you just observe that out of these many photons, you have smaller number of photons in the output. Well, in this picture, you send these two photons, but you get just one out of them. So how this is possible? Then, certainly one of these photons just disappear. But where does this photon go? Microscopically, what happens is if your material is absorber, then you send a certain frequency of light, then you send certain energy of photons, and the material, of course, consists of some atoms, and we know all atoms has some energy levels, right? And these energy levels can be just depicted like this, these lines, and lower lines are lower energies, higher lines are higher energies. If your atoms inside the medium has its lower energies, and if one of these photons just disappear, then what it means is that these electrons at the lower energy levels just gets energy out from one of these photons they absorb, and they promote themselves to a higher energy level. This is what happens, okay? And microscopically, how this absorption goes is this. The material, usually you'll see that the material that absorbs light eventually heat up, right? They will heat up. That's heating up coming from these energies, extra energies of these electrons, because they just get energy from the light. This is how the medium inside your car, if you put your car, even in the winter time, in a day which has sunshine, right? You will, when you enter your car, the car has, you will find your car very, very warm inside because of the greenhouse effect. But the thing is, outside is very cold. Then how come this warming up happened? This is the way. The energy coming from the sun, the high energy photons coming from the sun, they just are absorbed by the materials inside. But when they absorb by the materials inside, the materials heat up. But this heating, since the car is closed, I mean, no any windows are open, all the doors are closed. They're not giving up this heat easily. So that's why you find your car heat up even in the very cold winter days. What if you have sunshine, of course. I mean, this is the way. This is the way the energy transfers from the energy of the light to the materials by this method. The material has its electrons promoting in themselves into higher energy levels. They get higher energy, extra energies. And also, of course, the electrons, when they get this high energy, they just, collide with themselves or collide with other electrons with this high energy. So the kinetic energy is inside will increase. That's kinetic, increasing kinetic energy of the molecules and the atoms will reflect as the heating up of the material. Okay, so this is the way that these absorbers, sorry, work. I'm trying to get rid of the work in the microscopic domain. Okay, this is the explanation in the microscopic domain. All right. Sorry. I was here. Okay. All right. So, and this picture, when the time is up, we have 7-minute time, 8-minute time. I will stop the lecture anyway. Okay, let's look at this picture. So what you see? Well, these E stand for the energies, for the energy levels for the atoms inside the medium, inside this absorber. But of course, you know that you don't only have two energy levels, you have many energy levels. For the sake of simplicity, we only show only two of them over here for the atoms. So you send these photons and one of them is absorbed. What do you get? Well, you send this picture over here, this graph, intensity versus time, etc. This intensity level is the level of the intensity of your input light. Okay. Sorry, this horizontal axis is not the time. The horizontal is just the frequency. My question to you is that, if you have such a energy levels in your medium, in the optical absorber, do you always get this absorbance? Always get this absorbance for all frequencies of the photons that you send? Now, your photons are absorbed only if each and every energy of these photons corresponds to the energy difference between the levels of this medium. Okay, if you get your energy of the photon just equal or close to the difference of these energy levels, that photon will be absorbed. If not, it will not be absorbed. And what you observe over in this picture in the graph is that. So this level of the intensity is just the level of the intensity you send to these medium, but as you go along this direction, the intensity, you just change the frequency of the intensity. Whenever you come to the right frequency, by what I mean by right frequency is the frequency of the difference between these energy levels, and that frequency, let me put it down over here. You can calculate the corresponding frequency. How you can calculate the corresponding frequency? Let's call that frequency to be 12 f12. This frequency is nothing but E2 minus E1 divided by H. Let me put over here. The frequency 12 is E2 minus E1 divided by H. So these E's are energy levels of the atom, the first and the ground state energy and the first energy, or ground state is not zero always. And this H is the Planck constant. If you divide this energy difference by the Planck constant, you get the hertz, the frequency. And if the photons are having this energy difference, then they will certainly be absorbed. But if not, not. Because you see over here in this picture, your incoming light has some intensity, but it is not absorbed because the frequencies of this part is a way larger than the frequency between these two energy levels difference. It only occurs, it happens at over here. And also, you see, not all of the photons are absorbed. So if all of the photons were absorbed, then this dip will hit to zero. Okay, and there will be no output photons. All of the photons, in that case, will be absorbed. Well, what it means is that you must have very high number of absorbing material, so that and also if you send you know not very high in compared to as a number of photons in compared to number of atoms in the medium, all of the photons you might think that they will be absorbed. Well, this tip will be very much close to zero. But if you have, usually that happens, very high intensity in compared to number of atoms inside the material, not all of the atoms, photons will be absorbed, because there is not enough atoms to absorb all of the photons. That's why your signal will not drop to zero value, but some value which is larger than zero. Okay. If this is the case, just halfway through, then certainly that this is the case, that you just send twice the number of photons, you get the number of atoms inside the medium. If you have twice the atoms, the photons, then only half of the photons will be absorbed, of course. If all of the photons are meeting with the atoms, of course, there's also this condition that your photons must, overlap with the location of your atom. Otherwise, if it passes by, or it's out of focus, then it will not be absorbed, of course. Oh yeah, this picture tells you this. All right, this is the absorbance spectrum, you might call. You send very different frequencies of light, but you observe only certain frequencies are absorbed in the spectrum. Okay, this is the signal coming from spectrum. You have some source of light that you can change the frequency. You just observe by changing the frequency. You observe the input and output light. Whenever you see this decrease in the intensity, at that point, this frequency, you can say that atoms has that certain energy, because they absorb this energy of photons, or this frequency of photons. So this is the way also to analyze the energy levels of the atoms in a medium, and it might be gaseous medium, etc., whatever. But sometimes you hear, right? Sometimes you hear that they discover a new planet, or a sun, a new star, etc., and they just give you this information that this star or this astrophysical object has this certain amount of nitrogen, this certain amount of oxygen, etc. How do they do this? They just get the light coming from this astronomical object, be it a star or a planet or whatever. It's planet atmosphere. Okay. For example, take it Mars. We know the composition of the gases in the atmosphere of Mars. How? We just collect the light coming from Mars, put it into spectrum analyzer, and observe these dips. Of course, there will be many dips, not only one dip. And there will be many dips in the spectrometer, certainly telling you that the atoms, or whatever the molecules on the atmosphere of the Mars, just shows absorbance at these frequencies. And you just get a fingerprint of this spectrum. That fingerprint, certain dips, the location of certain dips will show you what kind of atoms are in there. For example, if the nitrogen 2 levels just fits to that, nitrogen 2 levels only have the energy difference